today we will be covering on basic statistics and hypothesis testing only. So this will be again a short class like previous one. So before getting into this, let me recall something that we did yesterday. So something from there. Uh, so regarding set.seed. So in yesterday's class, as I said, if I set a seed to a certain number, the repetitive pattern or the sampling pattern would be same. So I have shared this code with you in the WhatsApp group as well. So if I set my seed as 1 and then if I take a sample from 1 to 10, so I'm getting this pattern. Again, if I set my seed as 1 and again I do the same thing and I'm getting the same output. So this is actually the utility of set.seed or sampling pattern. Now let's say I change it to 1 to 3 and then I take a sample. So this is my pattern at the moment, and let's say again if I change it to 1 to 3 and I make a sample in same pattern. So this is what set.seed does. The sampling pattern remains same, so that when I produce a sample again, it gives me the same output. So one more example, let me show you. Set.seed 1 2 3 4 5 sample letters, and from there I want 5 letters. So sampling seed is 1 2 3 4 5, and then so these are the small letters that I'm getting. So out of all the alphabets from A to Z, these are the 5 alphabets I'm getting. Now again, if I set my seed to 1 2 3 and then again I do the sampling, I will get the same pattern. So this is actually what setting seed does. So Arun just asked that is there any relation between the output that I'm getting and sampling or the seed that I've set? So in the last class, as I discussed, for example, suppose I have a sine curve. So let's say I've set my sampling pattern to 1 2 3. So the sampling pattern, what it will does is at a certain interval or at a certain with certain pattern, it will take the sample. So every time that I have set my set.seed to a certain number, sampling pattern will remain same. So if I have the same population and from there I am setting a sample after setting a seed, so my output will always. So that is the only reason that we are getting the same output every time with setting the seed. So yeah, if you are considering the same population and you want the same output every time, then setting dot seed is the best option that you have. So sampling will be of randomly only, but it will have certain pattern. So that is the main utility of set.seed. So this was regarding set.seed, and also one thing that I came across my video yesterday. So I might have said that about right skewed and left skewed oppositely. So this is something like my left skewed. So when most of my population are drifted towards the left side, it will be my left skewed. And one if it is shifted towards the right side, like this, then this will be my right skewed. Okay.
Yeah, Ankit.
Yeah. Okay.
Yeah, actually, when I seen your screen,
Hmm.
it will be this is just a opposite.
Okay. So yeah, that.
So yeah, yeah.
Yeah. So it could be that I've said oppositely, or I could have slipped my tongue. So even in the slide that was there, I mentioned that if it is drifted towards the left, it will be a left skewed. And for, let's say, if I show you my slide that was there. o- Okay, so here I have, so yeah, I have said it oppositely. So this will be my left skewed, and this will be my right skewed. So yeah, the longer tail will be towards left, and the longer tail here will be towards right. Okay. So thanks for rectifying me. Uh, 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 Mainly, we will be dealing with the hypothesis testing today, and uh, so let us start with some of the example and understand that how it works. So I'll start with a basic analogy, and from there we will take on and we will understand that how hypothesis testing works. Just give me a moment and let me set. Uh, like we have learned in our previous class that always representing the entire population won't be a good idea because my entire population could take a large number of values. So a better way of understanding this, always taking a sample and from that sample can understand whether my and what my entire population looks like. So here I have taken an analogy from my everyday life to understand that how this sampling works. For example, let's say I have a big piece of cake which I want on my birthday, and from that cake or a 50-pound cake which has been mentioned here, I want to take a sample and I want to understand whether my uh, cake tastes good or not, whether it would be a good idea to buy this cake or not. So what I will do is from that big cake, I will take a small sample and I will try to taste it. So there could be three outcomes that has been mentioned here. Um, the test piece is awesome and tastes like the best cake that you have ever had. It may be an instant buy decision. So instantaneously, I might feel like this is the best cake or the most wonderful cake I ever had, and let me buy that. So, and then I have another option of the test piece is contradictory to what your expectation was. So you expected that it would have tasted much better, but instead it is quite opposite to your belief. So in that case, you won't buy that. And another, we have a third case that quality is not the best, but still satisfactory. You want to buy it if nothing better is available. So this is another case. So depending upon other factors that I have, I will make my decision. So here are the three things that could be done out of my hypothesis. So even in statistical part, hypothesis testing is in the same way. Let's say I have a big population, and from there I take a sample, and I need to understand that whether my entire population also represents the same thing. So that could be tested from this hypothesis testing, and for that we have some tests available. So let us go through that and understand how it works. So there is a small example of how hypothesis testing works. So let's say we have a big population and from there we take a small sample, and from this sample we want to understand or we want to have a clear indication or trend that is there in the main population. So for that we take a sample and try to understand that how the entire population looks like. So these are the few steps that are involved in null hypothesis or the hypothesis testing. So the first step is to state your null hypothesis. That what is your null hypothesis and what is something that is quite genuine. For example, for suppose in the cake example that which I took earlier, my null hypothesis could be that cake doesn't look good or it is an ordinary cake. It is my only assumption. So as a general opinion, I'm taking that it is a general cake. My alternate hypothesis would be that it is a better cake or even the best cake that I ever had. So I will definitely go and buy it. So first you have to state your null hypothesis. For few of the tests, the null hypothesis is already provided with the test. So for example, beta test or that we have coefficient test in a linear regression. So there the null hypothesis is that the my coefficient that I'm having is not significant or not making a significant contribution towards my linear model that I have, or is not a significant variable. The alternate hypothesis would be that no, it is making a significant contribution and it has quite a significant impact on my overall model. So that is a beta test for significance of a variable in linear regression. And for there, we have something called p-value. So if a p-value for a particular variable is low, we reject the null hypothesis that it is not significant, and instead we claim that it has a significant impact on my overall model. So here, if we consider only for the cake, so we have a null hypothesis we have already declared. Then we go for the sample of that cake, and we make our assumption, and on that basis we test whether that sample looks good or not, and on the basis of that we make an inference. So this is an entire analogy to understand that how this testing hypothesis is done. So there are a few more examples which you can see here to just to relate and just to understand in a better way that how a hypothesis testing works. For example, bank customer salary. I made an assumption that average income is around $35,000. So I take a sample of some 300 customers, and on basis of that, I compute that what is the average salary, and then I make a inference that whether to reject my null hypothesis or to accept my null hypothesis. Similarly, it's a drug testing that my drug contains 1.5% of alcohol. So from the entire drug that I have, I take a sample of 100 milliliters, and from there I try to understand that whether to accept my null hypothesis or to reject it. Similarly, I have something like a customer satisfaction score, and on basis of that, I try to understand whether it is a good idea to accept my null hypothesis that the customer satisfaction level is above 80% or not. So, so these are the few examples. So let us move ahead and see how we can. So there is another example here for soap. For let's say we have an example of so there is an industry or a factory which produces tons and tons of soap every day, and I am having an assumption that every soap weighs around 250 grams. That is a standard weight of a soap, and I am assuming that, and it is an average for the for all the soaps. But here is a problem. So what happens is if my soap weighs more than 250 grams, then it will be a loss to a company. And sorry, if it is less than 250 gram, then it will be a issue for customer satisfaction because I'm promising my customers that it will weigh around 250 grams, but I'm not delivering the same quantity. Second would be it weighs more than 250 grams. So in that case, it would be a loss to a company because I'm expected to produce 250 grams, but instead I'm producing more. So I'm delivering more than I should have done. So in both the cases, I have a problem for my company. So what I will do here is I will state my assumption. I'll start with the assumption that my soap weighs only around 250 grams, and then I will take some random samples of 50. From there, if I calculate and try to understand that what is my average, the new average of the sample that I'm getting, and how likely it is to have a sample weight of 250, more than 250 or less than 250. So here it is the case. So my initial assumption was it was around 250. In the problem that we see now, we have come across with a claim that it is not 250, it is 260. So there is a claim from some of our members or some of in people who are working with this soap industry. They make a claim that no, it is not 250, it is 250. So how we can check that? So what would happen is there we need to understand few things. So we'll proceed with that and we will understand that how it is done. So these are some of the null hypotheses that have been stated, and these are some of the alternate hypotheses. So one thing that I may want to make clear that whenever we say that accepting null hypothesis or rejecting null hypothesis, this alternate hypothesis has been said only because we fail to reject the null hypothesis. So there is a difference. So, uh, based on the statistics and the p-value that we get, we can either accept or reject the null value, or sorry, null hypothesis. So, alternate hypothesis has been said because it becomes easier to understand that we are rejecting the null hypothesis and accepting the alternate or accepting the other assumptions. So, it is not that we have a different assumption, only that we are rejecting the null hypothesis, and to just to say it simpler, we are saying that it is an alternate hypothesis. So these are some of the example. For let's say the number of our customer base is 50% male, and our alternate hypothesis, or if we reject this null hypothesis, we have the percentage of male customer is not equal to 50%. Similarly, the average height of the country's female population is 5.5 feet. And what is the alternate? That it is not. Vaccination and flu are independent of each other, and others says it is not. So similarly, we have some null hypothesis and its corresponding alternate hypothesis listed out. So it is quite self-explanatory, and you might have got some of the idea that how it works. So here is something that you need to understand. That is central limit theorem. So what happens in central limit theorem? So let's say uh, in layman terms, let me explain you what happens is. So let's say I have a uh, this population of how much this is. So 1,000. This is lakh. So some 10 lakh I can see. So a population of around 10 lakhs, and from there I take randomly choose 50 samples. So from 10 lakh soaps that are produced every day, I take a 50 sample and calculate the mean. So I'm doing this for infinite number of times. So let's say I have this 10 lakh number of soap. I am taking 50 as a sample and calculating the mean. Again, I am taking 50 as a sample and calculating the mean. So on repeatedly until infinite times. Just to see that how the distribution looks like. So what central limit theorem claims that if I am doing this process, the distribution of mean that I have got so far will be a normal distribution. That will be irrespective of the parent population. So let's say what my parent population was, or what was the distribution of my parent population, or the average of all the average of weight of all the soaps. So that is irrespective. What was my distribution here? That is not relevant. But here, what central limit theorem says that if I'm calculating the average of all the samples that I've got, my distribution will follow a normal distribution. So this is a major assumption of a central limit theorem, and we actually find it true. So when you test it, so like I've said, if you keep on doing this test and proceed till infinite time, you will find that your distribution that you have got will be a normal distribution, and most of your population will be concentrated around 150. Okay, so this will be most of my population where it will be concentrated, and with increasing and decreasing numbers, it will keep on varying. So this is the main basics of central limit theorem. Okay, so like I was saying here, so I have a population of around 10 lakh soaps that are produced every day, and from there I'm taking a sample of 50 and calculating the mean. So here I have taken a sample of 50 and calculated the mean. Again, for some other 50 soaps, I've taken them and calculated them in. And I've continued this process for infinite number of times, a lot many number of times, so that I can have a respectable or a good amount of numbers to uh, make a claim that how my distribution of mean looks like from a sample. Okay, so what central limit theorem says that if I do it infinitely, the mean that I have got from each and every sample, if I make a distribution or a density plot of that, I will get a normal curve, or my curve, the resulting curve would be normal in nature. This is my central limit theorem. So, the definition is the distribution of means of large samples tends to be normal, regardless of the distribution of the parent population. So, irrespective of what was the population of the soaps that we have got, my central limit theorem, or the distribution of mean that I have, will resemble a normal values. So as I increase the number of samples, or as I increase the number of that distribution that I have taken, or number of samples that I have collected and mean I have taken, so more the number, more it will resemble a normal curve. So it depends upon, so it tends to become normal. So if you do it infinitely, it will become a normal. So that is what my central limit theorem says, and this is how it will look like. So if I'm claiming that it is near to 250 grams, then this is how my normal curve will look like, and most of my population will be concentrated here. So this is my
Yeah,
basic working of
got it.
central limit theorem. So any questions?
Okay, thank you.
Okay, okay,
No, got it.
okay. Thanks a lot.
Got it.
Okay. So these are the few distributions that I have that I'm expected to get. So uh, mainly if I'm considering for bank customers, and I'm claiming that I'm having a null hypothesis that average income is $35,000, and I'm taking a sample random of 300 customers. So my sample distribution is expected to be a normal distribution, or what we call a bell curve. In most of the industries that that appraisal cycle happens and bell curve comes into picture. So most of you will be aware of that bell curve. So normal distribution is something of similar to bell curve, or it is same. My t distribution is actually something which is a flat type distribution. It remains more or less flat. So it has a bulge somewhere like this, and it goes down. Not as steep as normal, where it goes like this. But t distribution is somewhat like a flat one. So again, we have chi-square distribution and F distribution. So there are certain constraints with or certain working with that, but mostly in things like linear regression and other assumptions of linear regression, when we work with, or when we check the error of linear regression that we have got, normal distribution is that what we look for. So in most of the cases that we come across later on, for most of them we will be working with a normal distribution. So in next few slides, I've listed out how this distribution looks like and how is the distribution for each of them. So let's say this is what my t distribution looks like. So mainly t is only there for when degree of freedom is still 30. After that, it will start resembling my normal distribution. So this is let's say for 1. For 1, it will be like this. So that's why it is said that for t value or t test, it is preferred that my number of degree of freedom or number of samples that I have is 30 or less than that. For more than that, Z score does the work. And if I keep on increasing after 30, I am expected to have a normal distribution. So see, at degree of freedom when it is 1, it is more like a bulge or has been is a bit down. So and as when I keep on increasing till I get my normal distribution, it is much steeper compared to uh, the previous values. Similarly, this is for chi-square distribution, though I've never worked with this, but this is how it looks. So for n equal to 1, I have a very steep value, and later on it goes. And I think as I increase in number, it will start resembling the other distributions. So standard normal distribution, like what we call a bell curve, and this is
Ankit,
yeah.
yeah,
So these are the generally my so here let's say for students that I have just mentioned, t-test is actually done for two cases. When my sample is less than 30 and also I don't know the standard deviation. Or I think there was something missing. So I remember that it was less than 30 and when the standard deviation is not known. For then t-test is done. Otherwise, when I have a large population and I know all the standard deviation, my assumption value and my expected value, then z-test is done. And there we have a chi-square test for categorical to categorical variable. Yes, Darshan, that is correct. Sample size less than 30 t-test and sample size more than 30 then z-test. That is absolutely correct. And chi-square test is mainly done for two categorical variables. So let's say mm, so let's say an example. Uh, I have two variables. Uh, let's say mm, one is male, sorry, gender. One is gender, and another is my smoker or not. So it will be a flag variable. So mainly it will represent 1 or 0, and gender will represent 1 or 0. So in both the cases I have categories. So in that case chi-square test works. So this is actually to check whether my both the population has any significance variance or there is some relation between them or not. Because if both are continuous variable, I can take a correlation matrix or I can make a correlation between them and I can understand that how both of them are related. But in case if it is a categorical, I don't have that liberty. So in that case, my chi-square test works. So taking this soap example, so getting back to that soap example that we were discussing. So here my assumption is that my population has a mean of 250, and with the claim that 260 could be the main value of the sample that I have. So I'm conducting with this Z test. So here, this is my expected mean value, or which somebody has claimed, which is, and this is my normal mean value that I have, 250. This would be my standard deviation and number of observation that I have. And on basis of that, I have got a Z score of 14.14. So what does this mean, and how can we make a prediction on that? So what happens is there is a table for Z score. So with every Z score value, I have a corresponding P value. So you can go through a table of Z-score, or you can search on net. The results that you will be getting from that is for every Z-score value, you get a corresponding probability value, and how likely is that if my distribution follows a normal trend, then with a certain Z value, what is the probability that it will be belonging to the sample range. So here there is something called significance range, or significance value of 5%. Let me, so here, so this is my entire structure of the normal distribution that I have got so far, and I've expected that my mean should be here. So mean should be here, but with a z-score of 14.14, I'm getting a range of somewhere like this, or very small probability. So with a z-score of 14.14 and above, my p-value, or the probability value that I'm getting, is 1.54 into 10 to the power minus 44. So it is very small value. So it is highly likely, or it is very unlikely to have a uh, have 260 as a main value. So for generally we accept a null hypothesis, or I would say we accept this assumption that if it is there is a significance level of 5%. So if it exceeds that value, or if it is less than, my p-value is very less than that 5% of significance range, then I will reject the hypothesis. So here my hypothesis is that this 250 is my sample, and with the p-value that I've got, I can claim that yeah, 250 is correct. So the assumption of having 260 as the main value is incorrect. Okay. So hope here it makes sense that how this value is obtained, and how we have got to the conclusion that our mean is not anywhere near to 260, it is near to 250, and 260 is way beyond our normal range of expectation, and 260 can be easily rejected. So this is a typical example of a two-tailed hypothesis. So this is a critical region. So my main assumption is anything which is so if I'm getting a p-value less than 5%, so that means 2.5% here and 2.5% here. So this is called a two. Okay, just a minute. So
Ankit, if you
yeah.
can give you the example for two tail, just to
Okay.
understand.
Okay. Okay. So for two tail, let us say. Uh, so let us say that I have taken any value. Okay, just a minute. Just a minute. So okay. So two tail, what it would be. So So let me explain this. So here, what my z-score? It was 14.14. Okay, and let's say if I'm getting a negative z-score. So if I've considered that 240, then I'm getting a negative z-score. So if I have to consider that mod of z value or modulus of that z value, plus or negative, I don't care. I only consider about the magnitude. So magnitude of that z value, if it is more than this, then I'm in a good range to accept or reject my null hypothesis. Or sorry, actually reject my null hypothesis. So what was the significance level there? 1.96. So modulus of that will take care for both the side. For let's say now, if I've taken only for positive case, if I have to take for negative case, instead of 260, I will write it here 240, and I will get a negative z-score. And negative z-score will take care of the left hand side tail. Right now we were only working with the right hand side tail, but if I have a z-score of negative, it will take care of the left side of the tail. Okay, but let's say I only need to consider my population which is near to my main, only near to 250. In that case, I have to consider both positive and negative, both sided tail, because I need to check that how much confidence I have to have in, or I'd say any distribution which is near to my main value. For that reason, I need to check for both on positive and negative, and there I will get a modulus of z value, and on basis of that modulus of z value, I'll try to understand that what will be the p value I'm getting. So when we will be doing with our linear regression, there you see there will be a value of p corresponding to modulus of that z score, corresponding to modulus of the t value. So for that, what happens is the linear regression, what it does is it checks the assumption for both the side, both the tail, and then it is able to explain. So is it okay?
Oh, yeah, Ankit, yeah, fine.
Yeah.
Thank you.
So Akshay also made a so provided this in a comment that let's say here I have a null hypothesis that my mu is equal to 0, and the alternate hypothesis that it is not equal to 0. So here I was making only a claim based on a certain value of 260, which is how much it is different from 250. But here what I am doing is I'm checking that if my mu is equal to 0, then how close it would be to 0, whether I should accept or reject the null hypothesis. So in that case, if my expected or my assumed mean is 0, then anything away from 0, whether it is positive or negative, I have that should be considered in two-tailed, right? So yeah, thanks Akshay. That was a very good example that you have provided. And also, as I was saying with this for min, that if I've considered my min to be 250, and if I check a condition of plus minus 10, then my range automatically becomes 242 to 260. So here what I'm checking is how close my value is to 250. So thanks Akshay for that comment. So this is mainly a bit of understanding on critical region and critical values. So critical value would be my, if I'm taking the two-tailed, my z-score will be modulus of 1.96. Okay. So these are the typical scenarios and what are the tests that we will be carrying out. So there is a list of it, and this is quite self-explanatory itself. For example, as I said, the large sample that I have taken, which is more than 30. and my standard deviation is known, for that we'll carry out z-test. If it is small and I don't know the standard deviation, then t-test would be carried out. Now, dependence of two variable that, like I said earlier, if I have a categorical on both the side, then chi-square test. Yes, sir, correlation test will be when we will be dealing with linear regression. So there is something called, is there any correlation between my dependent and independent variable? So that will be tested through Pearson correlation test. Test of beta, as I said, it is actually test the significance of a variable, whether it is making a significant contribution or not. So beta is mainly a coefficient test, or if I'm having a certain value of coefficient, then how much significant does it make? So then beta test, what is my null hypothesis is that beta is equal to 0, or my coefficient is nothing, that this variable doesn't make us any significant impact. On the other hand, I have a alternate hypothesis which says that my beta is not equal to 0, or that variable does make a significant contribution. F test also is for so F score or F that we get is also for model. Also we get if for a model there is a, for example, if we are running a linear regression model, so we will get a F score there, and on basis of that we get a p value also. So having a p value there with less than 5% will actually give us the understanding that whether this model does have a significant impact, or it is really relevant to use this model forward or not. So,
Yeah, Ankit, can you explain the correlation test?
okay, okay. What is correlation test is different from test for beta. Okay, okay. So test for beta, we will come to that. So just so let's say, so here is my x and here is my y. Now if I make a correlation x comma y, so I'm getting a correlation of 97%. Now let's say if I'm making a correlation of x and x, then I'm getting 1. That is 100% correlation that I'm getting. So both are same. So 100% correlation means both are along the same line, or you can say a linear curve. So if I make a plot of my x, so this is what I will be getting, a completely linear curve. But here in the other case, what happened is x comma y. So this was a actually square curve, or the variance was square. Okay. So for that reason, the correlation value dropped down. So still there was a correlation, but lesser. So this is what a correlation actually means. That and for that case, both of them have to be a I would say a numeric variable. So let's say here it was. Now on the data set that we have here, let's say for year 2004 and 2003, is there any correlation between the 2 years? So I think that dataset is not there, or it is not able to fetch that, because otherwise it would have suggested me. So okay, let me import the dataset and then explain. So here, if I'm making a correlation that for the year 2004, and if I have any relation between 2004 and 2003. So here I'm getting a correlation value of 57%. And if I see a plot for both these years, so see, so it has been scattered like this. So only if let's say if I would have removed these outliers, so this is a quite extreme value, and I would have considered only this, then it would have become quite a linear kind of variation, and my correlation value would have been quite high if I would have excluded these values, because then it would have resembled quite a linear relation. So this is what a correlation does. So formula for correlation is I think covariance divided by some variance of x and variance of y. So for that I need to check also. But yeah, this is how it works. And if you want to find correlation here in R, this is how it works. So any more questions regarding this? And yeah, regarding as Swati said, that beta test. So what happens is if I have made a linear regression, so here is my A plus B of X. So this is a simple linear regression formula that I have. So this is my simple linear, and here this is my beta value or the coefficient that I have. So depending upon that, I have a null hypothesis. My H0 would be that my B equal to 0. And now if B equal to 0, then that this variable X doesn't make any significant contribution. It is as good as removing this variable. So this is my actually beta test, or the test for having a significance of this X variable. My alternate hypothesis is that beta is not equal to 0. That no, it has certain value and it does play a significant role in determining my value of y. So this is mainly in a nutshell, this is my beta test, or my test for having a significance, or whether that variable has a significance impact or not. So Akshay asked, when trend is not linear, how can uh, no so beta value, no. So what happens is this value that I am getting, so only assumption is that equal to 0, not equal to 0. That is all. So yeah, so slope, you know that it can take a value from minus infinity to plus infinity. So there is no uh, limited range for that. Only thing is that when slope becomes 0, my dependency on x also goes away. x becomes as good as nothing. So that is the only assumption here. Whether how much impact it makes and how much significant it is, that comes later on, and we will see that also, that how much weightage or how much dependency we should have on a particular variable. And so Akshay, you asked that when suppose it is not linear, then what we should do. So there are few transformations that we need to do. For example, so if anyone has gone unmute, please mute yourself if you're not speaking. Okay. So what happens is when trend is not linear, so like for example here, between x and y, the trend was not linear. Okay. So here I need to make certain transformation. What I can do is I can square root of y. Now if I do, I'm getting a linear value, right? So in that case, when my data set is not linear, I need to make certain transformation. For example, let's say I have another value. My value started with this, then it went like this, and then there was a steep rise. So I need to accommodate all of them. So what I can do is I can change the scale of my variable. Here what I will do is I will introduce a log. So putting log here will actually change the scale, and it will be in a different scale. So in that way, most of the or the high variation that I was getting, considering only the linear value after logarithmic transformation, more or less it will reduce the scale. So these are the transformations that you can always do or to improve the non-linearity trend that you have in your data set. So for that you need to analyze and need to understand that what would be the most suitable transformation that can be done. So, so few more things. Uh, Normality is something different. So as Arun asked that if my distribution is not normal, so what I can do with that? So for normal log is one of the transformation, yeah, which you can use to as a one step towards getting into normal, but having done the log transformation won't always guarantee you that it is absolutely normal. The basic assumption that we have is in linear regression is that our data set or the variable that we have chosen should be normally distributed, but I've worked on many those data set, and getting a normal distribution is very hard, and you can expect that it won't be possible at any stage that you will get a normal distribution. So in those cases, what can be done? As I said, if I'm having some very extreme values, I can put it down in my particular range. That I can do. Log transformation is also to put them in the same scale, but that will not always guarantee that my resulting distribution will be normal always. Normalization is one of the techniques, but normalization is of no use when it comes to linear regression, because as I've seen results of linear regression after normalizing and before normalizing my data set, and it was same. So that won't create any, or that won't be of any use. So normalization is one of the technique where I can normalize my data, and but in perspective of linear regression, if you're saying, that is not going to make a difference. So, okay. So So last few things for today. That errors in accepting or rejecting the null hypothesis. So there is mainly a type 1 error and type 2 error. So quite basic things that what is my type 1 and what is my type 2, and which error should be given more priority or more weightage and which should be given less priority. For example, let's say I have to assume that a certain person, or say I'm dealing with one of my students, and they have said that I have taken a loan but I have not defaulted. So there I need to classify my null hypothesis. So let's say on basis of that I have made some assumption that my null hypothesis is that that person has not defaulted, and I'm sticking to my. So just a minute. So all of you are facing that issue. For so let's say as I was saying about a person. So let's say that person has taken a loan. My null hypothesis is that that person is not going to default, and my and what I've done is after my inference. So there is some issue. Let me check that.
Yeah. Yeah. Previously you mentioned about the beta test.
Mm-hmm.
In beta test we mentioned that null hypothesis if beta equal to 0.
Mm-hmm.
So it means it means we are checking the independent variable are contributing or not.
Yeah, correct.
This, okay.
Yeah.
Thanks.
So as you have seen here, the coefficient of the independent variable is 0 in regression model. So here if you see the slide as well, I mentioned that beta test is mainly the test for coefficient, or the value is, or that variable, that coefficient. If the, as I've said earlier, that if the coefficient is 0, then automatically the dependency of that variables goes away. So this is only that the beta test is all about. And for beta test also there are few steps that after beta step, then there we calculate standard error. After standard error we calculate that t value, and on based on that t value, when then again we calculate the p value. So ultimately the p value that we get in a linear regression model, so that at the end summarizes whether this variable is making a contribution or not. So there are few steps related to that, and slowly we will understand each and every step there. So regarding the case which I was talking about, so let's say I have made an assumption that a person has taken loan, and my assumption that the person has not defaulted. So that is my null hypothesis, that person has not defaulted. But that in reality what happened is the person has actually defaulted. So so accepting my null hypothesis was an error. My null hypothesis was false. uh, and another case would be, I have predicted that that person has uh, what so the person my null hypothesis was the person is not a defaulter. And according to my inference, I have made a claim that no, the person has defaulted, and I have rejected my null hypothesis, and I have accepted my alternate hypothesis. But what happened is, uh, instead, it was true that the person has not defaulted. So you see, first I have accepted the null hypothesis, and then there was an error, and now I have rejected the null hypothesis, then there is another error. So after understanding the situation, what do you feel is the most dangerous error, or most impactful error that could be? out of the two cases. So just apply your common sense and understand that this is the situation and which error I should avoid. Yeah, Akshay, anyone else? So anyone please try, Swati, Arun, Nitin, uh, or sorry, Vinay. So here I've taken two situations. First of all, I've said that the person has taken a loan, and my assumption was that my null hypothesis was he has not made, he is not a defaulter, and I've accepted my null hypothesis, and my final inference was he was not a defaulter. But instead, what happened is my null hypothesis turned out to be wrong. My inference turned out to be wrong, and I got an error in estimating. Another case would be my null hypothesis was that person is not a defaulter, but on inference and on scrutiny, I found that the person is a defaulter, and I rejected my null hypothesis and accepted my alternate hypothesis, claiming that the person has defaulted. But instead, what happened is the person was not a defaulter. So in both the cases, I got it wrong. So first, so one was my type 1 error and another is type 2 error. Now in that case, what happened is when in these two cases, which would be most fatal or which would be most impactful, the classification of a innocent one, or sorry, the culprit as innocent, that would be most vulnerable or most impactful for me, because I want all my culprits to be identified properly. So suppose if a person is a defaulter and I am able to identify him correctly, then it would be a good scenario for me. It will be a helpful scenario for me. But instead, if I'm not able to identify my culprit, then it might be a revenue loss for me. So you need to understand that in these two errors, that which would be most impactful for you. So here are a few cases that I've listed down, and we will understand one by one that which makes a better impact. So let's say testing whether a drug is poisonous or not. So the type 1 error is rejecting the null hypothesis, saying that the drug is not poisonous when it is really poisonous. So rejecting the null hypothesis, saying that drug is not poisonous and when it is really. So this is and accepting the null hypothesis, saying that the drug is poisonous when it is really not poisonous. So there I have two cases. So what could happen here is the drug is poisonous, my null hypothesis, stating that the drug is safe and might yield serious consequences. And here my type 2 error is stating that the drug is unsafe and might not cause a big damage. Similarly, here also we have a testing whether a customer is good or bad before a huge personal loan. The similar example that I just explained now, that a customer is good or not. So my initial assumption is that my customer is good. Now I've rejected the null hypothesis. So you might what would be the consequences? You might get a good customer and the profit associated with that customer. So I'm losing out on something, some small scale. But if I approve that loan to a bad loan, then it might help impact a huge revenue loss for me. So in this case, type 2 error has a greater impact for me, and I always tend to avoid this type 2 error at any cost. So this was all about today's session on hypothesis and hypothesis testing. Yeah, like Vijay Mallya loan. A nice one, Arun. Yeah, correct. So that was a good example. So, like I said earlier, that there is a difference between accepting the null hypothesis and accept an alternate hypothesis. So this is a noteworthy point that is there. That so yeah, Akshay. So this is the most impactful. So if I am approving a bad loan, then it might create a problem. So this type 2 error is fatal or has a most significant impact on my business compared to this type 1 error. I might lose a good customer, but any day I might get it again. But if I'm having a bad loan approved, then that would be a severe of serious consequences. So drug is poisonous. You can understand that if someone is taking a poisonous drug, then so where it could land up. So in that case, you can consider that which case is more fatal. So lastly, this is the ending note and noteworthy point. Though we are using the phrase accepting the null hypothesis, when really testing, you don't really accept a null hypothesis. You either reject the null hypothesis or fail to reject the null hypothesis. We used accepting the null hypothesis to make it easier to understand. So this is the main phrase that you need to understand, that though it seems quite similar in terms, but instead what actually happens is we reject and we fail to reject. That is what actually happens. So this is all for today, and if you have any questions or any query, we can take that. So Akshay, I hope this is clear that here, as this is the negative null hypothesis that we have taken, that the drug is poisonous. So type 1 error is more fatal. And here, as our null hypothesis is a positive one, that the customer is good, type 2 error becomes more fatal. Yeah, correct. So anything that you want to ask, and we can discuss. Uh, Otherwise, we can wrap. So deciding your null hypothesis is entirely on. See, here that my null hypothesis, I could have taken it the other way around as well. Here I've taken that the customer is good. I've taken it. I could have taken that in other way around. I could have taken that my null hypothesis is that customer is not good, and on basis of that, I could have checked. For so only thing is that for tests like beta test, Shapiro-Wilk test, the null hypothesis is already stated. But for uh, general understanding, for your explanation, these examples are taken. Like for example, drugs is poisonous or customer is good or not. So, in for general cases, if you are working or in a business scenario like this, so you need to take your own call, or you need to understand that how it should be taken.